Well, hello and welcome back to Engineering 202 as we endeavor to work our way through experiment number 2. As we go through this, you'll see that a lot of what we're doing is very similar to experiment number 1, but one difference is that we're going to change the frequency so we can hopefully make some conclusions about how frequency affects impedance. So let's go ahead and get started with that. This may not show up that great on camera, but I'm going to be sending hard copies of this to you, so I think that will hopefully help you with that. We're going to be looking at two circuits here going through this. This circuit here with the impedance of a capacitor, and this circuit here with the impedance of an inductor. And really, we want to concentrate on just this last branch here with the capacitor and the resistor, or with the inductor and the resistor. So that's going to be what we're doing. Our source voltage is here anywhere from about 2 to 6 volts peak to peak. We don't really have to keep a consistent voltage. Whoops, I'm off the screen there. Sorry about that. We don't necessarily have to keep a consistent voltage. As long as we know what the voltage is, it'll show up in the trace. We'll be able to deal with that. And then we're going to be running at a much higher frequency. Last time we were at 60 cycles. We're going to be running at 10 kilohertz and 30 kilohertz, and see how that changes the circuit. We've got a variety of component values here, some 100 ohm resistors and 10 k ohm resistors. In a moment here I'll write down what the actual values were. Then the capacitor is 0.1 microfarad, and I'm going to just take it on face value. I will note that it has a plus or minus 10% range, and as we go through some calculations, that may become important. And with the inductor, again, I'm going to take it on face value also. But I will note that the resistance, I've just took the inductor, I measured the resistance of it. Let me grab that thing here. So this is a board of the inductors, and they're just, as you would imagine, coils of wire. It's very thin wire, so they can be damaged, so we usually try and put them on something so that they don't rattle around in the drawers and whatnot and get hurt. This was the 500 millihenry one that we used last time. This has an air core. Most of these are steel core. And this is the 2.5 millihenry that we're going to be using this time. So basically what I did is I put the ohm meter from this point to this point, and I measured the resistance of that, and that allowed me to get the internal resistance on that, and it turned out to be, let me get my notes here, 58.5 ohms. So we'll say R sub L is 58.5 ohms. Okay, and I'm going to tackle this lab a lot like I did the last lab. I'm not going to get too bogged down in the circuit and adjusting the scopes. I'm going to show you what we came up with when we did that. We talked in the last lab last term some about the oscilloscope, and I'm going to use the third lab that we do in here as an opportunity to go back and review that, for the simple fact that if I were to try and include all of the data analysis that we want to do, and also recapping the oscilloscope and everything, this video just comes out too long. I think once you start getting close to an hour, people start to tune out. So I want to just kind of pick my battles here. So those of you that are frustrated that you're not seeing the circuit, not seeing the oscilloscope in work, take heart. We're going to revisit that in laboratory number 3, and I'll talk more about lab 3 as we wrap up this one. So let me put some more values for you here. Like the last lab, I'm not going to give you a specific data sheet. You're going to need to pick it out of this video so that hopefully you watch the video. But this resistor here turns out to be 100 and 0.5 ohms, and these circuits are very much the same, so I'll just reproduce this down here, 100.5 ohms, and I didn't rebuild both circuits. I just took this element out and replaced it for that element. This turns out to be 9.84 k k ohms, and then this would of course be 9.84 k ohms. Then this one was 99.8 ohms, and this one would then be the same. I use the same resistor, 99.8 ohms. This inductor was 2.5. We'll just take it at the face value, 2.5 millihenries, and the resistance of that inductor, we already said, was 58.5 ohms. So I've got something like that. And then the capacitor, we'll assume that it has very little resistance and just take it on its face value, 0.1 microfarad, 10 to the minus 6 farad. So we've got that all documented. The way we're going to test this thing is I'm going to take this point down here as my reference ground. So I'll use the oscilloscope ground, attach it there, and I'm going to do very much like we did last time. I'm going to come in with channel 1 right there. And I don't know that we'll need it, but channel 1 would measure the voltage across this resistor and then also measures the voltage across the combination of those two. And then I will come in with channel 2 here, and likewise channel 2 there. Very much, again, like what we did last time. So this would then, hopping around here a little bit, this would then allow us to look at this circuit, and it's very similar to last time. With channel 1 here and channel 2 here with the ground there, I could then figure out this voltage across this impedance. And while we know these impedances, I mean, we could take and we could painted these flat black so we didn't know what they were and test them. But then we have a bunch of flat black things running around the lab, and it doesn't work very well later on. And I think there's some value to trying to, instead of just guessing blindly what we have, really working and trying to get to some known value. So we're going to use our measurements for channel 1 and channel 2 to try and figure out, is it a 0.1 microfarad? How close do we get to that? And here we're going to use our measurements for channel 1 and channel 2 to try and figure out how close we get to that. So that's what we're doing here. And again, just like last time, and I keep saying that, and it's really true, we want to reinforce these concepts, reinforce these calculations and things like that. So if lab 1 was confusing and didn't go well for you, hopefully by going through this again with just different numbers, we start to make things a little easier, and if lab 1 did go well, we cement that. So with channel 1 and channel 2, we can say that the voltage across this unknown impedance is going to be the difference between our channel 1 voltage, we'll have to pull that off the graph, and the channel 2 voltage. And I think we'll use this channel 1, we'll say that that's whatever its magnitude is with the phase shift. We'll take this, like we did last time, as a reference of theta equals 0. We'll take it as 0 degrees. Okay, so we'll find the difference between those. That's our voltage. And then this current, of course, the current that goes through this and this resistor, that's why we have that resistor there, sampling resistor. We'll take whatever we get for channel 2. And again, that's why I took the reference as 0, because we have to use this so much. We'll take a reference of 0 degrees here, divide it by 99.8 ohms. That's what that resistance was. Yep. And that's the current. Now with the voltage and the current, that ratio, we can get the impedance, and we will look at this as some resistive portion plus J, and whether that is omega L or minus, maybe I better be a little more general about this, say that this is let's see, how do I want to do that? I can just say that it's plus J omega L, or I could say minus J over omega C, right? Okay, so that's what I've got going on there. And I'll go through an example and try and cement that a little more. So that's what we've got there. I think this is in pretty good shape. The reason I allowed some variation here is the source is just not a very good source. So as you put different loads on it, it tends to change quite a bit. And rather than getting sidetracked with that, we'll just let that go. It's not going to change our experiment because we know what the value is. I think we've got that. I'll take our questions and I'm going to set those aside. So these are our questions. We'll come back to those as we wrap up the lab. So I think that's a good time to do those. I won't get sidetracked on those now. And I want to look at the data here. Okay, so this is the data. These are the pictures of the oscilloscope. And I'll be giving these again to you. They're actually in color when I give them to you, but I've tried to document the legends such that if you choose to print them out in black and white, or I don't know that anyone's not using a color monitor anymore, but maybe you have trouble with colors and whatnot, that there's some other distinction. So this is our 10 kilohertz with a capacitor. So we are back here looking at this circuit right here. So we've got this circuit here with the capacitor. We're at 10 kilohertz, and we've got 8 microseconds, so that's 10 to the minus 6 microseconds per division horizontally. And then channel 1, that's the larger yellow one, so that would be this one. That's 1 volt per division. And channel 2, you can see there's channel 1, there's channel 2. Channel 2 is a smaller one, but it's still 1 volt per division. So I'm going to come back and go through this one. That's just as good as any to go through. But before we do that, let's look at the other data. So we've got this one. That's the 10 kilohertz with the inductor. So now we've moved to and are looking at this circuit. Again, same frequency, so our time legend, we would think that that would be the same, 8 microseconds, 10 to the minus 6 per division. That's our horizontal scale. Channel 1 is 1 volt per division. That's the larger yellow one with these little spikes. That's some noise in our source. Like I said, we didn't have that great a source run on this thing. And channel 2 is the smaller blue one. That's this one. And those, again, are both 1 volt per division. So I will leave this one to you for you to work on. We'll come back and maybe have a couple comments on it before we run away from it. Then this one right here, we've moved to now 30 kilohertz. So we've increased the frequency by a factor of 3. We've gone back to the capacitor. And as you could imagine, our time scale has changed. So now we just have 2 microseconds, 2 times 10 to the minus 6, because the frequency is larger. And then channel 1 and channel 2, I've changed my story here just a little bit, because the scale on channel 1 is 1 volt per division, whereas the scale on channel 2 is 500 millivolts per division. So I didn't want to start saying larger and smaller, because is that larger with the scale factor or without the scale factor? So I said that channel 1 is the yellow one, if you're looking at it in color, and it goes through the origin. So we would see this as channel 1 right there going through the origin. And it looks like the smaller one, but remember it's represented with a different scale, so it is really actually the larger one. So that's why I avoided that nomenclature on this one. Channel 2 is the blue one, 500 millivolts per division. That's that one. And then finally, we have this one, which is 30 kilohertz with the inductor. 2 microseconds per division on the horizontal scale. And again, the channel 1 and channel 2 magnifications or scales are not the same. We have 1 volt per division on for channel 1, 200 millivolts per division on channel 2. So this channel 1, we're told, goes through the origin. So this would be channel 1. So with that, let's see if we can go back to this first case here, right here, and get the information that we need from this. So we'll start with the capacitor and 10 kilohertz, and see if we can get the information that we need from that. So get my notes here. Now let's see. I think we'll start here at channel 2. So channel 2 is the smaller one, so this is the channel 2, so I need to try and find the magnitude of that. It looks like we've got about 1 division and a little more. I'll just say 1.1. So 1.1 and times our scale factor, which channel 2 is 1 volt per division. So this turns out to be 1.1, and I'm going to take that as my reference, so I'm going to say that that's 0 degrees. So this would then be my voltage of channel 2 right there. And getting things set up, of course, to come over here and put them in this sheet right here. So then channel 1, let's see what we have here. We could say that we have, that's the larger one, so it looks like I got 2 divisions. I think I can probably just safely say 2 divisions times 1 volt per division, which is equal to 2. And then this is going to have some phase shift theta. So before I can finish this up and say, well, the voltage of channel 1 is equal to 2 at something, I'm going to have to go and figure out what that angle is. So let's go and do that. So I think I'll go ahead and to figure out the frequency here, that's an intermediate step that we're going to need. I'm just going to use this wave here, and I'm just going to look at 180 degrees of this. I mean, you could do the whole thing. You could measure from there to there, and that's 360. I like the way this is pretty close to 0. And so I can just measure 180 degrees there. So let's count that up. 1, 2, 3, 4, 5, 6. It looks like I've got 6 and some change. I think I'm going to call it about 6.4. So I'll say that I have 6.4 times 8, what do we have, microseconds, okay, which gives me what, 51.2. I'm going to double check that calculator here. Yeah, 51.2 microseconds, or if you wanted to, that would be 51.2 times 10 to the minus 6. Rather than having all of this scientific notation, I think I'll just leave the units there. So I could say then that my frequency, of course, is equal to 1 over the period. So I'm going to say that this is 1 divided by 2 times 51.2 times 10 to the minus 6. Now we need to go back and use the base units here, because we don't want to use the microsecond. So there's 51.2 times 10 to the minus 6. Where'd the 2 come from? Well, of course, that is because this was only for 180 degrees. It wasn't for the whole 360, so I had to multiply that by 2. So we'll go through the math there. This comes out to frequency. Oops, I'm way off the screen there. Sorry about that. I better back up and try and fix what I've done there. So we had 6.4 divisions. 1, 2, 3, and I'm off the screen there. Okay, so I had 6.4, 1, 2, 3, 4, 5, 6, 6.4, and I multiplied that 6.4 times 8 microseconds, because that was my scale factor up there, 8 microseconds. So 6.4 times 8 microseconds, 51.2. So when I go to calculate the frequency now, I've got 1 divided by 2 times 51.2. And again, this 2 comes from I'm only using 180 degrees. So I need one complete cycle. One complete cycle is 360, so that's why I have to multiply this by 2. So that's where that 2 is, and then this is just 51.2 microseconds. Okay, so this turns out to be 9,766. Yeah, let's take it at that. 9766 hertz. We don't really want hertz, so we're going to multiply that by 2 pi. So I'll multiply that by 2 pi, and we get then that the omega in radians per second, multiplying by 2 pi, is 61,359 radians per second. Okay, so that's our omega. So obviously we weren't running at exactly 10 K. We'd like to be at 10,000. We were only 9,766, but that's close enough. Again, we didn't have the greatest source, so it wasn't that consistent. But we know what it is. That's the important part. So we've got the omega. So now I can look at my shift in here. And when I go to look at the shift, it looks like I've got about 2 divisions. I mean, if you measure from there to there, you measure from there to there, you measure from there to there, you've got about 2 divisions. So I'm going to say that that is 2 times 8 microseconds, which gives me, of course, 16 microseconds. So I can say then by ratio and proportion that theta is to 16 microseconds as 180 degrees was to what? 51.2 microseconds. And because these are both microseconds, I can get those to cancel. And theta turns out to be equal to, I think, 56.3 degrees. Let me double check that. .25, yeah, we'll call it 56.3. That's good. Okay, so that's theta. So now I can bring that up here, and I'm going to say that it's minus 56.3 degrees. Okay, and the reason that's minus because I know this is a capacitor, and we'll talk a little more about that as we go along. So I've got this piece, I've got that piece. I think I'm ready to move on. So with that, let me jump back over to this thing and start putting some of these down here. So I can say that my voltage V is equal to the channel 1. We had that as 2 at minus 56.3. So 2 at minus 56.3 volts. And then I had to subtract off this channel 2 here, 1.1 at 0. 1.1 at 0. So that turns out to be equal to, how did I get 1.66 at minus 89.7. Okay, let me double check that. .66 minus 89.66, yeah. Okay. So I've got that. And incidentally, I mean, this is a great opportunity for you to grab your calculator and work these out too. I mean, to be successful in the upcoming examination, you're going to have to be able to do these numbers. It's always amazes me that students, they start out with their calculator kind of going, oh, how'd you get that? And pretty soon they're faster than I am on the calculator. So just got to grab your calculator and start figuring out how to do these on it. We don't want to turn this into a calculator class. But if you have questions on how to do this, you know, I think there's one of these where Google's your friend. If you have your manual, that's useful, but also there's a lot of videos, a lot of good websites out there on how to use your particular calculator to do complex numbers. So So we've got that one. Let's do the current. So the current I, that's going to be equal to channel 2. That's why we put the 0 there, because I had to deal with it a lot. So we're going to have 1.1 at 0 divided by this 99.8, which turns out to be 0.011 at 0, I believe. Make sure that's right. Yeah. Okay. And I'll just go ahead and leave that in my calculator. I'd probably want, if I was just going to write this down and then type it back in, I'd want probably some more significant figures there. Well, anyway, with Z, I know that my impedance of this thing is going to be the ratio of this voltage divided by the current, right? So I take this 1.66 at minus 89.7 divided by 0.011 at 0, and that turns out to be equal to, what did I have? 1509.6, so I guess we'd call that 1510, at an angle of minus 89.7, or I'm going to do this in a rectangular form, which is going to make a lot more sense. Let me get that. So, I think my numbers are way too big here. Let me run through these again. So we've got 2 at an angle of 56.3. Okay, so I'll double check that one. Okay, double checked that one. Yeah, I had messed up something. So that one's good, that one's good, that's good. Then I am at 150.9, so this is 151 at an angle of minus 89.7. Now I'm going to switch to a rectangular form, and this turns out to be 0.879 plus, nope, not plus, minus J, minus J, 150.96, we'll just call it 151. These would both be ohms. This polar form is not as useful for us right now as this rectangular form. So again, I'm off the page here, my apologies. But let's recap where we are here. So I calculated this voltage, which is the difference between channel 1 and channel 2. I calculated the current. I then took their ratio, and I'd apparently typed something in or used the wrong number. I was off here a little bit. And you might say, well, how would I know that I was off? Well, I have a sense for the relative size of these, but in the next couple steps, I'll also show you how we'd know that we were wildly off. This number was looking to be, 10 times larger than that. And I'll show you in a moment how we'd see that that was a mess. So anyway, we take the ratio of these two numbers, and then I convert that. I don't want it in the polar form. I just convert it into a rectangular form, and I can then recognize, I mean, this is the impedance, so this is the resistance. So this versus 0, because we said we were going to take the resistance of the capacitor as 0. So that's not bad. I mean, that's fairly close to 0. That's a fraction of an ohm, so I am happy with that. This one here, remember, this should be minus j over omega c, right? So I can say that this is really that 151 is equal to 1 over omega c, where our omega, this is why we needed to calculate the omega. Remember back here we had this omega right here, 61,359. So let's use that. 61,359. So when I solve for C, boy, I'm having a hard time staying on screen. Okay, so the 151 is equal to 1 over omega c. I make my substitution for the omega, and solving that, C turns out to be equal to 1.08 times 10 to the minus 7, which, let's see, 10 to the minus 7, you could say 0.1 times 10 to the minus 6, so I could say that this is equal to 0.108 microfarads, right? Well, what did we say that our capacitor was? I mean, this versus what? 0.1 microfarads, right? That's about what? About 8% error, isn't it? So that's not bad. I'm pretty happy with that, actually. Remember that with our capacitor, we said that we were using one that was plus or minus 10%. I think I had mentioned that, right? Right over there, plus or minus 10%. So if we're, as long as we're not outside 10%, I think we can be really very happy with this. So I think that's pretty good. And you can see again what we're doing here is taking these measurements and using the measurements to figure out what we had in here. And of course we knew what we had in there, so then we can see how close we got to that, which we did a good job on this one. Okay, let me double check that. I think we're good there. A couple other things that we could do with this. If I look at this picture here, remember I have, let's see, what channel 1 is the larger one, so this was channel 1. And this is channel 2. Okay, and I could really say that channel, let's see, what do I have? I have channel 2 leading channel 1, don't I? Well, let's try and document that. I could say that channel 2 is proportional, I'll use the symbol for proportional, to current. Is that true? Yeah, I mean channel 2, there's our equation for current. We just take channel 2 and divide by a constant. So certainly it's safe to say that channel 2 is proportional to current. And I can further say that channel 2 leads channel 1. Let's look at that. So back over here, what we've got here, I've got channel 1. And if we look at it right in this range here, we would say that this wave would be leading that way, right? So this is channel 2. Channel 2 is leading channel 1. That's how I can make that comparison. Channel 2 leading channel 1. So channel 2 leads channel 1. Well, channel 2 is the current. So I could say that I is leading channel 1, which is the voltage. We'll call that E. And that's our ice, isn't it? Okay, which is the capacitor. So this is all this is all working out nicely. Well, let's go to the question sheet and see what we can do with this. Draw the impedance triangles. Here's our question sheet. Draw the impedance triangles for the C and the R3 branch. That's what we're working on here at 10 kilohertz. Well, I haven't done the 30 kilohertz, but I have done the 10 kilohertz. And what's that going to look like? We've got it right there, 0.879. So probably going to need some more room on this, but we'd have something like this. So there's our impedance triangle. And this is 0.879, 0.879, and minus 151. Okay, so I would have something like that. That'd be the impedance triangle. And for the 30K, are we going to expect the same triangle? Probably not. We might say that we'd hopefully have the same resistance. It's probably not going to be the same resistance, but hopefully it'll be a low value of resistance. But this isn't going to be the same. Well, I don't think so, because remember, this term here is based on omega. So we've got the omega in there, and at 30K, omega is definitely going to be different. How about the impedance triangle for the inductor? Well, I'm not going to go through that. You've got the data. You can go through that. But those triangles are going to look something like this, where you're going to have the resistance of the inductor and got the theta there. And then you're going to have what? The omega L, right? And as it goes from 10K to 30K, you're going to expect that to change. I'll calculate X sub L at 10K and 30K. So that's really just this piece of your, I mean, when you have the two impedance triangles here, you're going to take the omega L from this one at 10K and this one at 30K. So take this value and this value, that's all that's looking for. Draw phasor diagrams for the current through C and R3 branch and the voltage across it. Well, we should be able to do that. That's why I tried to document this. There is our voltage right there. And here is our current. So let's see what that looks like. So at 10K, I probably want to start out with some nice straight lines. And you can expand on this. We've got quite a few questions here, and I've kind of crammed them together. So I've given this to you in a Word document. You can expand on it. But let's see where the voltage is. That was 1.66 at minus 89.7. So there's our voltage phasor, 1.66 at minus 89.7 volts. Okay, and then our current is 0.011 at 0. So our current is like that. I will check that number, yes. Okay, so that's our phasor diagram. And when you do the inductor at 10K, you'll be able to come up with that. Do we have the current leading the voltage here? I think we do, don't we? So this would again be a good example of ICE for the capacitor. Okay. Well, good. Those are the questions. I wanted to go and look at the data just a little bit more. When I went through this, I just did the first case for the capacitor at 10K. If you look at the inductor, and this is also at 10K. One thing to notice on this, and in lab number 3, the next lab that we do, we're going to see this actually in real time. We're going to see the waves cross, but here we have channel 1, and then channel 2. And what do we have? Looks like channel 1 is leading channel 2, right? I mean, here with this one, we had channel 2 leading channel 1. Channel 2 was leading channel 1. And then on this one, we have channel 1 that is, let me get that right there. Yep, channel 1 is leading channel 2. So we would see that this would then be our Eli, or the voltage would be leading the current. So you can go through the calculations on this, very similar to what we did with the capacitor. The one thing with this one, of course, is that your voltage 2 here, you're going to take this as some magnitude at, I would recommend your 0 angle, and this one is going to be some magnitude at whatever your theta is, and make sure that that is a positive angle because it's an inductor. This one, then we go back to the capacitor, and we're running a higher frequency. The one thing that I would caution you on this, I went through these numbers already. When I got down to my impedance here, I'm not going to spoil the surprise too much for you here, but I got a small negative number, okay, small negative number, minus J, and then this 1 over omega c term, okay? And this small negative number really just comes from errors in reading this graph, okay? So I had just a handful of ohms there, but it was a negative value, okay? So just a warning there. You may be better at reading the graph than I did, and you won't have that problem, but if that does come up, and we talked about that on the last laboratory also, don't think that you've found some new phenomena or something. That just comes from the error in reading the graph. And finally then, this one, we go to 30K with the inductor. So that will allow you to wrap this whole thing up. I think if I look at the question sheet, then you'll be able to fill in these other pieces, because you're going to do the capacitor at 30K, so you'll be able to draw the other impedance triangle. You're going to do the inductor at 30K, so you'll have that one. You'll be able to compare these two. We've got this one. You'll be able to do this one, and you'll have it wrapped up. Like I said, you'll probably need some more space here. Make sure that you're doing real neat work here. Use a ruler. You can do this electronically if you want. If you don't, do it on engineering paper, and then take a good picture of it and cut and crop it in here. I was looking at the first labs, and a lot of you are doing a lot better than last term on those, so that's great. Keep up the good work. Well, I've mentioned laboratory number 3 a few times. Before we do lab 3, we've got an exam, so I'll give you some information on that and talk about that. But laboratory number 3 is going to be a little different in that I'm going to get you more involved in the circuit, get you more involved in the oscilloscope. It's going to be a lot of fun, because if we have a trace, maybe something like this, we're going to get to see this thing go from inductive to capacitive, that is, to see these waves cross each other, to see that this point actually ends up over there. So that's going to be kind of fun. But before we get into that, you're going to need to do some calculations. So keep your eyes peeled for an email that talks about what calculations that you need to do, and get you going on that, because we want to calculate it, and then we're going to, I'll show you how to measure it, which is going to be pretty easy, and hopefully again that your calculated values come up fairly close to your measured value. So that's where we're going with the examination in the next week, and then laboratory number 3 after that. So Good luck finishing up laboratory number 2, and good luck in all of your studies. Take care till I talk to you next time. Bye-bye.